So since we learned about a line, now let's learn about the other structure which we studied in high school, circles. And of course, as usual, we learn about a circle in 2D and its equivalent concepts in 3D and higher dimensional space. First, let's understand 2D. Let's assume I have two axes. Let's call them x and y. Or for simplicity, let's call them x1 and x2, whatever way you want. So a circle, so this is my origin, right? This is my origin. So let's assume I have a circle which is centered. I didn't draw it properly, but just bear with me. I'm a bad artist. So let's assume this is my center of the circle. Let's assume the radius of the circle is r. Then the equation of the circle, like any point lying on the circle, can be written as x square plus y square equals to r square. Here remember, the center of the circle is the origin, right? If the center of the circle is not origin and something else, let's assume the center of the circle is, let's say, h comma k, then the equation of the circle becomes x minus h square plus y minus k square equals to r square. This is the equation of a circle whose center is at h and k. Just for simplicity, let's assume, just like the way we assume that our plane goes through origin or passes through origin, let's assume our circle is centered on origin. So the math becomes elegant, right? This is the equation of a circle. Now let's assume I have a point P, right? So let's assume I have a point P which has x1 comma x2, right? Now, how do I determine whether a point lies inside a circle or outside a circle, right? Actually, a circle also separates your region, here in this case your 2D space, into two regions, things which are inside the circle and things which are outside the circle. So given any point P with x1, x2, if I just do x1 square plus x2 square, if that value is less than equal to r square, if that distance, if this value is less than equal to r square, then this implies that P lies inside your circle. Inside the circle. Inside the circle that is centered at 0, 0, which has a radius r. If x1 square plus x2 square is greater than, less than, so if it's strictly less than, then it's inside. If it's equal to, it's on the line. So if it's greater than r square, that implies that your P lies outside the circle. And if it's exactly equal, if x1 square plus x2 square is equal to r square, then P lies on the circle. Lies on the circle. That's very simple to show, right? Suppose if I have a point here, let's call this P dash. Okay, what is this x1 square plus x2 square? It's nothing but this distance, right? Because this is its x1 and this will be its x2, right? Of course, if this distance is more than r, because we know that for a circle, every point on the circle is at a distance of r from the center. That's how you define a circle geometrically, right? Circle is nothing but it's a combination of points which are at equal distance r from the center of the circle. Right? This is very, very straightforward understanding whether P lies inside a point or outside inside a circle or outside a circle. Now, since we understood about circle, let's extend this understanding to other types of into higher dimensions, right? So what we saw here is 2D, right? Let's move on to slightly more interesting thing. What happens in 3D? Suppose if I have 3x1, x2 and x3. Suppose I have 3 dimensions, x1, x2 and x3, right? If I have a circle or a sphere, the equivalent of a circle in 3D is a sphere, like a ball, right? Your ball, which is centered around your origin now has 3 dimensions, 0, 0, 0. And if your sphere has a radius r, the equation of such a sphere like this is nothing but x1 square plus x2 square plus x3 square equals to r square. This looks very similar to your equation of a circle in 2D, right? So the extension of the concept of a circle is a sphere, and this is how it looks. Now your question is, what happens in n-dimensional space? In n-dimensional space, let's assume I have my axes as x1, x2, so on, so forth, xn. Then, simply speaking, my n-dimensional sphere has a formula which is x1 square plus x2 square, so on, so forth, xn square equals to r square. This is the equation of a hypersphere. It's called a hypersphere. This is the equation of a hypersphere in n-dimensional space. right? This you can write it more concisely as I equals to 1 to n, xi square equals to r square. This is the equation of a hypersphere in high dimensional space. Remember, we understood about a hypersphere by just learning about your 2D geometry. Again, to repeat myself at the cost of repeating myself multiple times, this is the elegance and beauty of linear algebra. This is how linear algebra is applied to solve real world problems very elegantly when we can't visualize these high dimension spaces. Now again, just like in 2D, whenever this value is less than equal to r square, it lies inside the circle. Whenever it's greater than r square, it lies outside. Whenever it's equal to r square, it lies on the circle. Similar concepts for an n-dimensional hypersphere. If your summation of xi square, if it is less than, suppose for example, suppose your summation of xi square, I going from 1 to n in an n-dimensional space, if this is less than equal to r square, then the given point pi, so suppose here I'm assuming that your point p is x1, x2, so on, so forth, xn. If it is strictly less than r square, then your point p lies inside your hypersphere. In this case, your hypersphere is centered at origin and it has a radius of r square. Similarly, with greater than and equal to, the same interpretation that we learned in 2D can be extended to higher dimensional spaces.